So today we'll do a new chapter that is on nuclear physics. Okay. So there are many things related to nuclear physics like the nuclear force, mass energy and nuclear binding energy, and then size of nucleus and all that. Okay. So those are more theory. You can read through it. Okay. So we'll just touch upon the things where you can find some numericals. Okay. So those theory part like the size of nucleus, boundary binding force, and all those are more theories. So you
Yeah.
can read through it and just find out some of the important points and remember those things. So what is more important is where you will have numericals, how do you derive those formulas quickly, and how do you apply those formulas for solving numericals. Okay, mostly. So in nuclear physics, mostly you will get this radioactivity and nuclear fission,
Decay law.
nuclear fusion, nuclear reactor. So these are some of the important,
Decay law also.
yeah, radioactive decay. Okay, half life, whatever we are. So I'll just quickly go through those things. Okay, radioactivity, half life, nuclear decay, and then nuclear reactor, nuclear fission,
And
nuclear
fusion.
fusion, and what is controlled nuclear
Comes
reaction.
under nuclear fission and
It's
fusion.
nuclear fission it comes under, but so mm, you are like whatever in a nuclear fission process, if you don't control it with the help of controllers and moderators, so three neutrons are getting generated. You are trying to slower or try to control two neutrons and only one neutron you are allowing to escape. So one neutron will be, so it will be a controlled chain reaction. It will not be uncontrolled chain reaction. Okay. So atomic bomb is uncontrolled chain reaction. Okay. Whereas nuclear reactor, what we are using for generating the electrical power, that is controlled chain reaction. Okay. So with the help of moderator and like the control rods and all, we try to reduce the some of the neutrons whatever getting created during the nuclear fission process. You are trying to out of three neutrons you are using only one to
Yeah.
carry out the subsequent reactions. Okay, so uh, a huge amount of thermal energy gets generated during nuclear fission. So in a nuclear reactor, whatever thermal energy is getting generated, that is being used to, like say, in a thermal power plant, conventional thermal power plant. What is happening? They are kind of so in our NTPC or so we need water, like say in our place from river Brahmani they are taking water. Okay, so in Talcher area we have coal. Okay, so they will use coal and water to produce the steam.
Steam.
Okay, so basically that will happen in a component in a it will happen in a boiler. Okay, so what does boiler do? Like boiler, you have a combustion using the coal and the water that is taken from the river. It will get converted to steam. Okay, so that steam will convert low pressure, low temperature water to high pressure, high temperature steam. Okay, so when you steam has high pressure and high temperature. Okay, so when it has the capability to have high pressure and high temperature, so that steam goes to the turbine. Okay, so that steam goes to the turbine and the expansion happens in the turbine. So uh, so that turbine, when the expansion happens in the turbine, it will that is like turbine is a work giving device. So you will get some work output. So that work output will be in the form of rotational energy.
Yeah.
Okay, so that rotational energy turbine shaft will rotate and it will get coupled to a generator.
Yeah.
and that generator armature will rotate inside a magnetic field and you will generate current. Okay, so that's how your power plant functions. So in case of thermal power plant, you will have this boiler. Okay, and this water, coal and all, and steam and all. So in a nuclear reactor also you need steam also. The steam is common between them,
Yeah,
but how you are generating the heat, that
that's
only is different.
different.
Okay, so you have same boiler, but the heat you are generating here is by nuclear fission process. Okay,
There it is by
there it
burning
is
coal.
like say coal. Okay,
Burning
so
coal.
coal chemical energy is getting converted to thermal energy there. Okay, so by combustion.
Yeah.
Okay, here the heat is because of nuclear
Nuclear
fission.
fusion.
Okay, so yeah, so you can see like and now there is a trend to go towards nuclear power. So
Yeah.
the countries those who are having more and more let
Uranium.
us say you are having more and more uranium, thorium, and those kind of radioactive material. Those are very costly and those are very rare. Those kind
Quantities,
of
yes.
elements like uranium, thorium, and all. So those are like their atomic number is very high. Like say uranium 92 is the atomic number, and 235 is their mass number, right? So uranium, thorium, and there are many radioactive elements. So you know those are all F block elements.
Yeah.
So if you refer the periodic table, you have S block, P block, D block, and F block. So F block, which comes at the bottom. So you will find those radioactive elements there, right?
Yeah.
Remember?
Yes, I remember.
Remember the
Transition.
periodic table where
Yes.
does the uranium,
F
thorium, and
block.
F block, right? So
High elements not commonly found. All F block elements are radioactive in nature.
radioactive, yes. So those like you might have heard recently during the Russia-Ukraine war.
Alkanoid actinoids, they're called.
Russia-Ukraine war recently, like Russia had attacked one of the nuclear power plant. That was a dangerous thing because this nuclear power plant. Okay, so it is that power plant
Building
is
it
a
is very expensive.
building is very expensive. Also, that wall of that wherever this nuclear
If
fission is
that is
happening, it will
damaged,
be surrounded by a very very thick
1 meter
wall,
wall.
1 to 2 meter wall. So your thickness, so it is such a thick wall. Okay. So that there is no radioactive emissions should not come out, and because radioactive emission, as you know, like in
Can cause
19
cancer.
yeah, in 1945 when USA attacked Japan, that time it was a atomic bomb. Okay,
Yeah.
so what it is very very detrimental for human health. Okay, this radioactivity, it can cause cancer, and it
Cause
can
genetic
it can
mutations and
spoil generations together.
yeah,
Okay.
because of genetic mutations that will continue.
Yeah, mutations. Yeah, it will continue for generations. So that is so that's why it is very very important. The radioactive substances, the radioactive emissions are contained. Okay,
Yeah, they're
so it does not
controlled.
goes out. Okay, so that's why like when India we shifted for nuclear power plant. We have more nuclear power plant mostly in Tamil Nadu. Okay, in Tamil Nadu, I think Kalpakam, though we have a nuclear power plant. Okay, so we have in India we have not gone too much into nuclear power, but we used to depend mostly on thermal power because we have a lot of coal in our country, and you have hydropower. Okay, so this nuclear power means with little mass of radioactive substances you will get a good amount of power. Okay, that's why the trend is to go towards nuclear power. And you know thermal power using coal and all, it causes lot of pollution. Okay, so everything has its own advantages and disadvantages. Okay, hydropower is very good because there is no pollution, but the efficiency of hydro turbines are not that great. Okay. Uh, okay, so we'll start with radioactivity. Okay, so So we'll just quickly go to the important things. Okay, so there are three types of radioactive radiations. Okay,
Yes.
one is
Alpha, beta,
alpha ray, beta ray,
gamma.
and gamma ray. These are three types of radioactive. These are three types of rays which are which will be emitted during
Nuclear, yeah.
from a radioactive substance. Okay, so alpha ray is nothing but a helium nucleus. Okay, a helium nucleus,
Helium
alpha
atom.
decay in which a helium nucleus is emitted. So alpha ray is nothing but a helium nucleus. Okay, so it is nothing but 2He4.
4.
Okay, so this is a helium nucleus. So when and another thing is that the alpha, beta, gamma radiation does not take place at simultaneously. Alpha is getting then after alpha, beta, not
Yeah.
together. Okay. So then beta ray. Okay. So in which electrons or positron particles, in which the electrons or positrons, but with charge exactly put to that of electron are emitted. So here positrons are emitted. Okay. Positrons. Okay. So what will happen when a beta ray gets emitted? Your atomic number will increase by one, right?
Yeah.
Your positrons will
Mass
have,
remains unchanged, but
Ah.
charge, that thing changes.
in which electrons positron with the same mass as electrons. Okay, so the mass will remain same. So this positron will have same mass as electron, same mass as electron.
But its charge is opposite.
Same mass as electron. That means mass of electron is almost zero, negligible,
Yeah.
right? Your proton and neutrons have mass, but electrons does not have any mass. So beta ray is similar to positrons. Okay, so beta ray is positron. So when a beta ray gets emitted, your atomic number will increase by one, but mass will remain same because it's a positron which does not have any mass. So mass will remain same. If a beta ray gets emitted, the mass will remain same, but the atomic number will increase by one. Mass remains same, but atomic number increase by one. Clear? That is beta ray. Okay. Then gamma ray. What is gamma ray? In which high energy photons are emitted. Okay. So gamma ray are nothing but photons. That is positron. These are photons. So these are high energy photon. High energy photon. Clear? So high energy photons are emitted. And this energy of these photons are in the range of some thousand, so kilo electron volt. So
Yeah.
this is their energy. Okay. So just remember, like there can be a question. Okay, what is alpha, what is beta, and what is gamma? So why is it important? Because you don't have to solve anything. You just have to remember, and within seconds you can answer.
Yeah.
That's why it is important to learn all these things. Okay. Then we'll go to law of radioactive decay. Okay. Law of radioactive decay. Okay. So the law of radioactive decay says, okay. So the rate of decay is proportional to the number of atoms present at that point of time. Okay, so it's you are saying, let's say at any point of time you have n atoms. Okay, at any point of, say, at time t you have n atoms. Let us say at time t you have n atoms. Okay, so I am telling my rate of decay is nothing but dn by dt.
Minus dn by dt.
Minus dn by dt. Okay. So is directly proportional to log n, right? So if this is the case, that implies dn by n is equal to minus dt, right?
Yes.
So
Then integration.
So when you so this is not like, say, right? So this actually this equation you can authorize right as dn by dt is equal to lambda n. There is a constant. So
Yeah.
when you want the proportionality sign, when you want to change it to equal sign, you have to multiply it with a constant. Okay. So your dn by n is equal to lambda dt, right? Minus lambda dt.
Yeah.
Right. So now you integrate it, right? So now you integrate it. So you know your integration of dn by n is nothing but your ln n. What is ln? Ln means it has a base of e. Okay. Log has a base of 10. Ln has a base of e. So ln n is equal to minus lambda t. This is my derivation. Okay. So if I give a limit of n1 to n2 and t1 to t2, right? The limit of integration. Clear? So if this is the case, then this become ln n2 minus ln n1, right?
Yeah.
Is equal to minus lambda t2 minus
Lambda
t1.
t1.
This is your equation. Okay. So ln n2 minus n1 is nothing but ln n2 by n1. Clear? ln n2 by n1. Then lambda minus lambda into t2 minus t1. This is the equation, right? Okay, so in general, if it starts with n0 and goes to n, like we want to write a generalized equation, initial is n0 and at time t it becomes n. Okay, time t it becomes n. Okay, so this will become minus. Yeah, so it will become this n2 you can replace by n, okay? And n1 you can replace by n0. N0 is initial, okay? So it becomes ln n by n0 is equal to
t minus t0. Lambda t minus t0.
So lambda minus lambda t minus t0. Okay. So if we consider that at the beginning the time is 0. If time is 0, this becomes minus lambda into t. Right. So my ln n by n0 is equal to minus lambda t. So this is the okay. So this equation you have to remember. Okay. So using this concept you can find out what is actually half life. Okay. So half life is nothing but the time taken for the number of atoms to become half. Okay. So that is the time taken for number of atoms to become half. Okay. So in that case, let's say ln by half, right?
Yeah.
Ln by half is equal to minus lambda into t half, right? This is t half. So t half will be equal to t half will be equal to ln half divided by lambda, right? So t half, so this is the equation to derive half life. So t half will be equal to ln half
By
divided by
lambda.
lambda.
But then lambda will get cancelled if you substitute t half in this equation.
Lambda will get cancelled. Ln half divided by lambda. So you want to find t half. What is the formula of half life?
0.693.
Huh. So okay, so it's minus.
Okay.
So ln half it means what? It is ln 1 minus ln 2, right?
Yeah.
So this is my lambda. Okay. So you know ln 1 is equal to 0.
0.
So this minus cancels. It becomes ln 2 divided by
Right.
lambda. So ln 2 is what? 0.693. Okay. So t half, just remember this much only. T half or half life period is equal to ln 2 by lambda, which is nothing but 0.693 by lambda. So this is my
formula for
half life. Okay, so you will get numericals on half life. You can take a picture of this, then we will solve one numerical related to half life. We will solve one numerical related to half life, which will give you better understanding. Half life is what? The time taken for number of atoms to become half. Okay.
The initial amount.
On the initial amount. Okay. Just see what it is. Okay. So with this we'll try. So you have to remember this. Okay. Right. So this alpha, what is this lambda? Lambda is a radioactive constant. Okay. So lambda, it is mentioned what is lambda.
It will be for, it depends on material.
It depends on material. Right. Okay. So you have understood what are alpha, beta, gamma rays, And if one alpha ray get emitted, what will happen? If a beta ray get emitted, what will happen? If a gamma ray get emitted, what will happen? And now we have derived the expression for half life. Okay, so just remember T half is equal to 0.693 by lambda. Okay. Where from the 693 comes? It is nothing but
ln2.
ln2, right? So this is my expression. Okay, then T half. Okay. So let us try to solve one numerical. Okay. Uh, okay. Can you read out? I am not able to read out. Okay. Okay. Let me put it straight. I'll read it. Okay. Tell me what is the question.
The half-life of uranium,
Hmm.
92 and 263, 238. That
92 U 238.
Yeah.
Okay.
Undergoing alpha decay
Okay.
is 4.5
Okay. That is the half life.
half-life. 4.5 into 10 power 9 years.
T half life. T half is equal to how much?
4.5 into 10 power 9 years.
Okay.
What is the activity of 1 gram of sample of uranium? 92-238.
Activity of
1 gram sample of uranium 92-238. Find rate, decay rate.
activity of 1 gram sample of uranium 92 U 238.
That means you have to find decay rate.
So you are telling my activity
Means
activity is nothing but
rate.
decay rate.
Yeah.
Activity is nothing but your decay
Decay
rate. Okay, which is dN by dt. Right?
Yeah.
So you want to find out your dN by dt. So dN by dt
It is proportional to dN by dt. It is equal to lambda n. R is equal to lambda n. Yesterday we derived.
No. What is activity? What does activity
Activity means rate. You have to find decay rate.
Decay rate. So activity I am telling you that is dN by
Okay.
dt.
Yeah.
Okay. So dN by dt we have derived it as e to the power minus lambda t, right?
Yeah.
Sorry, dN by dt. Okay. So we have earlier told dN by dt is equal to is directly proportional to n.
Yeah.
N. Okay. Number of atoms present. So now we want to find this term. So dN by dt, if you want to make it a constant, it becomes lambda n or minus lambda
Yeah.
n or whatever, right?
Yes.
So now I know my half life. So if I know my half life from that equation itself, I can find out what is lambda. Okay. So my half life is 4.5. So
You have to convert that first.
So T half is equal to 0.693 by lambda. Okay. That means my lambda is equal to 0.693 by T half. Okay. T half. Okay. If this is the case, then my lambda is equal to 0.693 divided by how many years?
We have to convert that.
Converted to what?
Seconds.
Second. So 1 year is how many seconds you can find out. Like say one day is 365. 1 year is 365 days, and 1 day is 24 hours, and then that is 3600 seconds.
It comes as 3.16 into 10 per 7. To convert
Lambda
years
is equal
into
to how much you are getting lambda? You see there in the book.
Lambda value. They've taken T half, they've converted it. So 1.4. They're using they're putting lambda as 0.693 by T half. They're not dividing it completely, so that simplification becomes easier.
Okay, whatever you know now, understand the concept. Okay, so you can find out lambda. If you find out lambda, then first you have, they are telling that it is activity of 1 gram sample. Okay, that means your initially your number of atoms. Okay, so
equal to Avogadro number.
Avogadro number. But are they trying to find it dN by dt is number of atoms per second?
Yeah.
Okay, if it is number of atoms per second, then you know my, like say my atomic mass is 238. Okay,
Yes.
my atomic mass is 238 here,
One.
and it is 1 gram, right? The
Yes.
total mass is 1
1
gram. 1 gram. Okay. So you have to find how many moles are there in it.
Yeah.
Okay. So like say 1 mole of uranium 92 238, 1 mole will weigh 238 gram, right?
Yeah.
That is the thing. 1 mole is nothing but your 6 point. Okay,
023
so 1 gram will contain how many moles?
Yeah.
So 1 gram will contain 1 by so 1 by 238 mole, right?
Into
238
Avogadro
mole.
number.
So 1 mole is how many atoms? So 1 by 238 into 6.023 into 10 to the power 23. These many atoms.
Yes.
Right?
This is N.
This is your N. So this is number of atoms. So which is N.
Yes.
Okay. So this is my number of atoms. Okay. So now what I have to do is, I know my number of atoms, I know my lambda. So I can find out by dN by dt.
Yeah.
Here.
Yes.
So you need to just understand the concept. Everything depends from this basic equation. Okay. Clear?
Yeah.
So I'm not going into details of it. Try to practice as many as
Yeah.
possible. Okay. So this curve actually is a exponential curve. Okay. So your n, and this curve, like it is an exponential curve. Say n is equal to n0 e to the power minus lambda t. That means it is exponentially decaying. Okay, so initially the rate of decay will be very high, but gradually it will decrease. Okay, so n is equal to n0 e to the power minus lambda t. Okay, so this is the exponential curve. So when it is plus, so a positive exponential curve will, a positive exponential curve, how does it look like? You know the difference between linear curve and then your parabolic curve and then cubic curve. You know how like the rate at which the slope. Okay. So in a linear the slope remains constant. Okay. In a parabolic the slope it is a square. In cubic it is parabolic is nothing, your quadratic equation,
Yeah.
that one. And in cubic it will be cube of this.
Yeah.
And this is
Linear.
exponential. So in exponential it will be kind of okay. Yeah. So how does it look like in exponential? If you draw a curve, okay, so this is my, okay, so with time, so if in x-axis I have time, okay, in y-axis I have number of atoms, okay, instantaneous number of atom n. So if this is like this, the curve will be kind of, so it will be kind of asymptotic. It will never become zero.
Yeah.
So when what happens, like, so if this is, let us say n, okay, let us say this is n0. Okay. So after half-life, so half-life will be somewhere here. Okay. So then this in the y-axis it will be n0 by 2. And in the x-axis it is capital T by 2. Okay, so sorry, not T by 2, T half-life. Okay, This is time is T half life. We write it as T half. Okay. So in T half life, the initial number of atoms will get reduced to half. So you can see this T half life. Then it will be kind of 2T, 3T, 4T like that. So yeah, 2T, 3T, 4T like that. So you can see the amount of decrement in the first half life is very high, whereas in the second half life the amount of decrement is only this much, only this much.
Decreases with the amount.
So in the third half life the amount of decrement is only this much, only this much, very little. So you can see initially it is decreasing in a huge amount, then like this. So it is decreasing in a huge amount, then it is decreasing like this, then it is still decreasing in a small amount like that. So that is the interpretation of this curve. Okay. So now you understood, we have solved one numerical, you can practice many more. Okay. Okay, then alpha decay, beta decay, gamma decay I have already explained you. So yeah, I will just tell about nuclear fission and reactor. So you take a snapshot of this and then we'll do nuclear fission and nuclear reactor. See these here like unlike your dynamics or kinematics, here in nuclear physics and all you don't have to go into too much of mathematics, okay? But you can easily, by remembering one formula only, you can answer many questions, right? So you should never leave this kind of chapters, okay? Okay, so now we'll do nuclear fission, right? Nuclear reactor is more theoretical. If you read through it, it is fine. There is no numericals involved there in nuclear reactor.
Yes.
But there can be questions on what are the different substances to use as moderator, what are the substances used for control rods, like say cadmium or something. Moderator like heavy water. Okay. So H2O, that heavy water has a different chemical formula maybe. So in our culture in FCI there is a heavy water plant. Okay. So yeah. So let us see what is fission. Okay. So nuclear fission, what happens? So you have a say you have a uranium. You have a uranium, uh, which is 92 U235. Okay. This is my uranium. So this is a neutron induced nuclear reaction is fission. Okay. So what is fission? Fission is neutron induced nuclear reaction. What is fission? Fission is neutron induced nuclear reaction. So an example of fission is when a uranium isotope is, so isotope you have to study in your periodic table, you might have studied what is isotope. Isotope is same atomic number but different mass. So you know, as per your periodic table, the property of a substance depends on the atomic number. It is a function of atomic number. So isotopes are, if the atomic number remains same, its property will remain same, but mass number is different. Okay, that those are isotopes. So an uranium isotope bombarded with a neutron breaks into two intermediate mass nuclear fragments. Okay, So, so let me say this is my uranium. Okay, so one neutron is I am, so neutron has mass 1, but neutron means it is neutral. It does not have any charge. So that's why charge 0, mass 1. Okay. So this neutron is getting, it is bombarding the uranium atom, one uranium atom. Okay. When you are bombarding, it will generate one beryllium and one krypton. Okay. So this will generate two molecules, two atoms. Let us say Ba and Kr. Okay. So the mass, as per rule, the yeah, so it will give rise to beryllium is 56. Okay, this is 56, the atomic number, and krypton,
It is not beryllium.
what it is called? Not beryllium. Whatever, I forgot. Whatever you should remember. Why should I remember?
It's Ba is not beryllium.
What it is? Tell what it is.
56 atomic number.
What is Ba? You tell. Okay. Okay. So whatever Ba. Okay. You refer the periodic table. What is Ba actually? Okay. So this is 56. Okay. Then Kr is 36. Okay.
It's krypton.
Krypton. So 36. And then the mass is
Ba
144.
is barium.
Barium, okay. 144. And then krypton is 89, right? 89. Okay. So you can see here 56 plus 36 is equal to 92.
Yeah.
That is remaining same. But your 144 plus 89, okay, that becomes 233. Okay, 233. Yes, sir. Yeah. So 233. So this is, but you can see here you have 235 plus 1. You have input as 235 plus 1. So mass, input mass is 236 unit. Okay, so this is input here. The input mass is 236, but the output mass is 233.
Yeah.
Okay. So there is, this, E is equal to mc square. Einstein told that E is equal to mc square. So here in this nuclear reaction, there is this mass is changing. There is a decrease in mass. Okay, so this mass E is equal to mc square. So that much of energy will get generated because of this. Okay. So because of this, huge amount of energy will get generated. So you are creating. So in addition to these three, okay. So the equation is like this: so 0n1 plus 92U235 is equal to 56 barium 144 plus 36 krypton 89 plus 3 zero charge. Okay. So it will produce 3 neutrons. Okay. So it will produce 3 additional neutrons. It will break and it will produce this 3 additional neutrons. Okay. So these neutrons are very, very high velocity neutrons. Okay. So these are the products. Okay. So I will just tell you the concept. So I have one uranium atom. I am bombarding it with a neutron. Okay. So I have uranium. I am bombarding it with a neutron. So then it will create, let us say, three neutrons. So this is one neutron, this is another neutron, this is another neutron. So it has produced three neutrons. Okay. So again 0n1, 0n1, and another 0n. These are all neutron, high velocity neutron.
Yeah.
So in my nuclear reactor I have so many uranium atoms, right?
They
So
will again attack.
when I am bombarding with one neutron, there are three neutrons getting created, like
It
three
will
neutrons
again
getting
further
created.
it
Okay.
3 more.
So if out of these three neutrons, if I try to reduce the velocity, moderate, and try to neutralize through
But it is
two
nuclear.
neutrons, I'll allow only one neutron to create cause further reactions. Then that will be a controlled chain reaction. Okay. So these so this will again hit another uranium. Okay. Then it will again produce another three neutrons. Okay. Then again you try to neutralize. Okay. So again you try to neutralize. Okay. And neutralize in the sense you try to reduce their velocity. So you just take control of this. You just take control of this. Okay. So 0 and 0 and 1, 0 and we just take control of this. Okay. So then again it will hit another uranium. Okay. Like this it will be a controlled chain reaction. Okay. Otherwise if it is uncontrolled, what will happen? These three will, one will become 3. So 1 will become 3. 3 again 3 will become 3 into 3.
Yeah.
9.
9.
Then 9 will become again 3 into 3 into 3.
27.
27. Then 27 will become like say 81, like that. So it will be uncontrolled. It will go on increasing and you cannot control it. But if you, with the help of moderator and control rod, if you are able to decelerate this neutron or you can control those two neutrons, it will be a controlled chain reaction. So this nuclear reactor, they use controlled chain reaction principle. Okay.
Yeah.
Whereas atomic bomb, they use uncontrolled chain reaction.
This is hydrogen bomb.
This is not hydrogen bomb.
Hydrogen bomb is okay. Atomic bomb is
This is hydrogen bomb. There is two things. One is fission, one is fusion. I am not taught you about fusion. Fusion is different. Fusion. When you go to fusion, then that is a different concept. But atomic bomb concept is nuclear fission. Nuclear fission, and why you are getting so much of energy? Because there are three masses are getting reduced, and mass E is equal to mc square principle. C is velocity of light. So velocity of light is 3 lakh kilometer per second. Okay. 3 lakh meter per second. So 3 lakh meter per second, C square into even 1 gram also, if you multiply by that value, it will be a huge amount of energy. And if you can compare it with the heart, how much thermal energy, if you convert it into joule you divide it by, convert it into calorie, like say 1 joule is equal to 1 kilojoule is equal to how many calories?
1.47.
Huh?
1.47.
1.47. No.
Yeah.
No.
1 kilocalorie.
1 calorie is how many joule?
1.47 per.
No. 1 calorie is not one. You refer your book. 1 calorie is 1.47. You refer it.
1.4.
Okay. The point is wherever it is written, you find out. Okay. 1 calorie is how many joule.
Okay.
What I am telling is you will find out from mc square. You will find it in joule. So you can convert it into calorie, because any fuel, it will have its calorific value. Okay. How many calorie of heat one can give, one fuel can give per unit mass. That is called calorific value. So this calorific value is nothing but chemical energy, heat, calorie. Okay, so mechanical energy is joule. So mechanical, when you are interrelating mechanical with the chemical thing, you have to convert from joule to calorie. Okay. So I have taught you this latent heat of vaporization and all that.
Yeah.
You have to go through it again. Okay, specific heat, latent heat of vaporization, okay, latent heat of melting. Suppose you are heating ice, so when it starts melting, the temperature will remain constant. So the temperature is remaining constant means what? The heat is changing it from solid to liquid. That's why you won't see the effect as change in temperature, but it is taking that heat for getting converted to solid, from solid to liquid. So that is latent heat of melting. Similarly, latent heat of vaporization. Okay, I think I have taught you, right? So this is, if I go on increasing the temperature, so the curve is something like this. Okay, like, so the here it has started melting. Okay,
Yeah.
let us say here it is solid. So the temperature will with time, that this is temperature. Okay. So if I am heating something with some heat source, and let us say this is a solid. Okay. Let us say ice. This is a ice block.
Yes.
Ice block is solid.
Yes.
So when I am heating, the temperature will initially increase.
Yes.
Okay. So it is not ice. Let us say some minus 10 degree centigrade ice. Ice is at minus 10 degree centigrade. So when you are heating with respect to time, the temperature will increase. Then at 0 degree centigrade, this will try to melt. Okay. So the amount of heat that is consumed for completely melting the solid to liquid, that is called latent heat of melting. Right? Then it has become water now. Then again its temperature
From
will
water
increase.
to blood.
Then it will reach the boiling point. Let's say at atmospheric pressure, the boiling point is 100 degrees centigrade. So at 100 degrees centigrade, this water will get converted to steam. So that is called latent heat of vaporization. So these latent heat and these things are measured in calories. Okay. So this, because these are, this we are measuring heat in calories, but work in joule. So this E is equal to mc square. How much energy you will get because of nuclear fission is nothing but E is equal to mc square. What is M? Like say here, how much mass I am is getting destroyed or whatever. Even mass is not getting mass. Equivalent of mass into energy is E is equal to mc square.
Getting converted.
This here you are finding that 3 neutrons are like say, right? So that is okay. So there are some examples. You can go through this. Those are more theory. So so now you understood what is fission. Okay. So fission is uncontrolled nuclear reaction. Okay. And so there is two types of fission. One is controlled, one is uncontrolled. Controlled is nuclear reactor or nuclear energy or electricity what you produce. Uncontrolled is atomic bomb. Okay. So when it happens, so 92 U35, so one uranium atom, one high speed neutron is bombarding on it and it is creating three neutrons. So this neutron, there is a device, there is a equipment called cyclotron. This high velocity, this neutron is a very high velocity neutron.
They call
So these neutrons
accelerate
are
charged particles in region of combined electric and magnetic field.
Yes, so that is cyclotron, you can refer it, okay. Then this nuclear reactor and yeah, so this is more kind of, this nuclear reactor is more kind of theory. There is not much numericals involved here, okay, so you just need to go through it and remember things, just note down few points, okay. What is the material of control rod, what is the material of moderator, what is the function of moderator and control rod in a nuclear reactor. So how okay, you can take a snapshot about it. I'll just draw what is a nuclear reactor and then we'll wind up. Okay, so so you in your entrance, no one is going to ask to draw it. In your view, it would have been useful, but still to develop your understanding, I am just drawing it. Okay. So this is just a diagram of nuclear reactor. Okay, based on thermal nuclear fission. Okay, diagram of nuclear reactor based on thermal fission, right? So I have explained you the nuclear fission principle. Okay. So inside this, so there are what are the different components? Okay. So here you can see there is a closed circuit. So this is going. This is so this is coming like this. This 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 is called coolant. Coolant is nothing but your water. So this will come. This is coolant. This is also coolant. Okay. So this is your coolant. So this is a closed circuit. The coolant enters. This so this is your core of the nuclear reactor, and you will have some kind of control rods. Some control rods. That control rods will decelerate the neutrons. Okay. So there are some control rods, and yeah. So this is your steam. Okay. This is your steam. Okay. So steam goes to turbine. Steam outlet, and what is coming inside, this is water in, steam out. Okay. So this is a coolant. So this coolant, so here actually the nuclear fission process is taking place. So here the heat will get generated. So this coolant, it may not be water, it can be something else also. So this coolant, the property should be, it should have good latent heat. It should be able to carry more and more heat. So this coolant takes the heat from this core, whatever heat is getting generated, and this coolant transfers the heat through a heat exchanger. Okay. So this whatever this symbol na, this kind of symbol, what you can see, this is the symbol for a heat exchanger or a condenser. Okay. Heat exchanger. I was talking to you about this in refrigerator. So in refrigerator you have a condenser, you have a evaporator. So condensation or evaporation process, they happen at a constant temperature. Yeah. So in your refrigerator you have a condenser, you have a evaporator, you have a throttle valve, and you have a compressor. Yeah. So four things are there in refrigerator. So in the nuclear reactor you have a heat exchanger where the coolant will take the heat from the core, where the nuclear reaction fission process is taking place. It will become hot. So it is hot coolant. Okay, this is hot coolant. This is cold coolant. Okay, coolant cold. So it will take heat. So whatever this hot coolant, there will be a heat exchange happening between this coolant and the water.
Yeah.
So thus this will give up heat now, and this water will become steam.
Yeah.
Okay, so when this water becomes steam, then this steam enters inside a turbine. So this turbine, we draw it like that because expansion happening. So this is like my inlet area, this is my outlet area. Normally in a turbine the outlet area will be more because expansion is happening. Okay, so this is how these are control rods. Okay, control rods. These are control rods to decelerate the neutrons or to neutralize them. Okay. Then the heat exchanger, steam, coolant. Okay. Yeah. And this external this is called a reflector. Okay, so the external structure. So this structure is so the coolant transforms heat to the working fluid, which in turn may produce steam. Okay, so working fluid is nothing but your water. Okay, so this heat will produce steam. Okay, then the core of reactor is the site of nuclear fission. So where in this core nuclear fission is happening. Nuclear fission is happening inside this. Okay, the core of reactor, site of nuclear fission. It contains fuel element in suitably fabricated form. So what will be there inside this core? Some fuel elements, either uranium. Okay, in a suitable form. Okay, it will be fabricated into a suitable form. Okay, the fuel can be say it is called enriched uranium. So this fuel is enriched uranium. So what you get from like mining, it may not be enriched. So you will try to increase its concentration. So it will called in enriched uranium. Okay, so this fuel is enriched uranium and fission is happening inside that. Okay, the fuel may be one that has greater abundance than naturally. So naturally occurring uranium may not have that kind of concentration. Okay, so you can enrich it. There is an enriching process of uranium. Okay, so the core contains a moderator to slow down the neutron. So what is the function of moderator? So this core will have some moderator also, not only control rod but all moderators.
Yeah.
Some heavy water or something.
Yeah, to control the.
So this normally these control rods are made of cadmium. Okay. So and it will have moderator to reduce the to slow them down. Okay. To slow down the neutrons. Okay. What did the moderator do? Moderator slows down the neutrons. Slows down the neutron. Clear? The core is surrounded by a reflector to reduce the leakage. So it's a very thick structure so that nothing leaks out. See, in addition to neutron, there will be some there will be some radiations also. So those things need to be contained.
Control.
Yeah, so the energy released in fission is continuously removed by a suitable coolant, not necessarily water. Some coolant will have different material.
For different.
Okay, working fluid is water, but coolant is different.
For different fuels, different coolant.
Yeah. So a contaminant vessel prevents the escape of radioactive fission product. Okay. A containment vessel. So this is kind of a contain. It will be contained. It will prevent radioactive fission product to move outside. Okay. So the whole assembly is shielded to check harmful radiation from coming out. The whole thing is being shielded. I was telling 1 meter thick wall. Okay.
Yeah.
So that no radiation will go out. Okay. The reactor can be shut down by means of rods. Okay. So these rods, these rods can it can go in and go out. Okay. So if you push it in, so it will prevent, you can stop the nuclear reactor using rods, so that whatever one electron is going for control reaction also, that one neutron, that neutron also it will prevent that neutron also. So you can shut down the nuclear reactor using control rod. So if somebody asks, how do you shut down the nuclear reactor? Using control rods. And control rods are made of cadmium, important. Okay. So the coolant transfers heat to working fluid, which in turn may produce steam. The steam drives the turbine and generate electricity. Okay. So like any power reactor, nuclear reactor generate considerable waste products. Okay. But nuclear wastes need special care for treatment, since they are radioactive and hazardous. So in any power plant there are waste. So you might have seen in thermal power plant, in thermal or in Talcher area, how much of ash is there.
Yeah,
So
very.
when combustion happens, coal combustion happens, there will be lot of ash generated. Similar things happens in nuclear reactors. So there will be lot of waste product. So that
Which
need
is
to be
very
handled
harmful.
very carefully. Okay. So elaborate safety measures both for reactor operation as well as handling and reprocessing the spent fuel are required. Okay. So when the combustion happens, the spent fuel, what do you need to do with the spent fuel, like asking this thing. The elaborate procedure need to be developed. Okay. These safety measures are a distinguishing feature of Indian Atomic Energy Program. Uh, an appropriate plan is being evolved to study the possibility of converting radioactive waste into less active and short-lived material. Okay. So, so there are some more on nuclear fusion. Okay. So this fusion is hydrogen bomb principle. It is just theory. You read through it. Okay. So it will be easier for you. Okay. Then controlled thermodynamic fusion. So we have covered fission. Then we will discuss about fusion, and you can read through it. Okay. So that's all. So we have covered. First we have covered what are the different types of radiations, alpha, beta, and gamma. Then we have discussed about half-life. Then we discussed nuclear reactor. Okay. Try to solve some numerical and try to write down the important points. What is control rod? What is moderator? What is the role of a coolant? What is the working fluid in a nuclear reactor? And how do you shut down a nuclear reactor? Why is it important to contain the whole nuclear reactor inside a thick enclosure? Why is it important to dispose the nuclear waste? Why
Properly.
there is a suitable procedure need to be developed to handle this nuclear waste? So these are very very important. These are important points that you should always remember. Okay. Okay. Fusion and other theory part that force in nuclear inside and nuclear force and all, those are mostly theory. You can just read through it. Okay. You should never leave any questions related to nuclear physics, because there is not too much of mathematics as it is there in kinematics or even in dynamics. Okay.
Yeah.
Okay. Thank you.